In this video, we're going to take a look at another representation for graphs. This approach is what we're going to call an adjacency list. So again, we have our graph, right? Graph up top, and this is the thing we're trying to store. So we have v vertices, right? So I have in there 5 vertices, and I could store some in a matrix, that's what we did on the other slide. But this is a kind of a different thought. Let's say that we have an array that's the same size as the number of vertices. Now, for every vertex that I have in that array, I'll store what is called an adjacency list. So I'll store a list that contains all of its neighbors, right? So that's our idea here, right? This is an adjacency list, an array that's the size of the number of vertices, and at each position we have a list to represent all the neighbors of it. Okay, that's the basic idea. And so you can see this on the right-hand side. So if we look on the right-hand side, we have basically our array here of size 5. So this is basically coming off of this over here, right? So 0 through 4 are the positions and the nodes. And you can see that basically at every position I have a list, right? So at position 0 I have a list containing 1. If I'm at position 1 I have a list containing 0, 2, 3, 4. If I'm at 2 I have something containing 1 and 4. If I'm at 3 I have something containing 1 and 4. If I'm at 4 I have something containing 1, 2, and 3. So basically at every different vertex in my graph I'm going to have this list that stores these are things that are next to it, okay? So this is our scheme here, right? So this has a different flavor than before. Before we had kind of this brute force thing where it's like this matrix, we're just checking every single, we can store every single possible combination of pairings. Here we're not doing that, right? Here we're basically just saying, write down who you're connected to, right? And do that for every single node out there. So this is what we're doing here, right? So this is a much, much faster approach, right? Well, okay, the speed is, okay, maybe the speed's about the same, but the amount of space is a lot better. So let's dig in. So the question there, right, is how much space do I need to do this, right? How much space do I need? Well, okay. I guess I have to ask you guys, what do you think? How much space in terms of tilde will this take? And do be a little bit careful. Okay, so this in terms of tilde will take the following amount of space. It takes v for the array, because the array has v elements, plus 2e. Now, when you were doing this on your own, you might have thought, oh, it's probably v plus e, right? You didn't get the 2 in there, but the 2 is in there. Why is the 2 there? Well, the 2 is there because I need to again record traversing the edges either way, right? So if I'm going to 0 to 1 or 1 to 0, right? I need to do both ways. And so you can actually get that here because it's like, well, looking at the adjacency list, notice that at index 0 I have 1. Over here at 1, I have 0, right? So I have to basically have that edge in there, right? That one edge, right? This is really a single edge in my drawing, but it has to occur in my adjacency list twice to represent traversing it from either direction, right? So it occurs in 2 places. So this is, maybe not ideal, but it's pretty good. I mean, remember, right, that we are basically going up against tilde of v squared. So linear versus quadratic, that linear is going to be so much nicer, okay? So this is really a much, much, much better usage of our space on our computer. Okay, so this is pretty nice. All right, so that's it for space. Let's see. Actually, before I go further, maybe I'll add another edge in here so that we kind of see how the picture changes. So let's say I want to do the same thing as I had before, which is I added an edge right between 0 and 3. Let's just update our graph and see how it maybe looks. So I'm adding an edge between 0 and 3. That means basically that I look at position 0, add 3 to its list. All right, so I can do that. And then I look at 3 and I add 0 to its list. Do that, okay? So that's actually just to add an edge, right? So those two give us that new edge over there. Okay, so that's pretty cool. All right, so moving along, does this thing support self loops? Well, here, right, maybe it's a little bit of trouble. So self loops, what do you guys think? How would we add them to this picture? So here I can add them by basically just throwing them in the picture, right? So here, if I want to say 0 is connected to 0, I just do this. Say 2 is a self loop. Add 2 to its own adjacency list, right? So all of a sudden I have my picture looks like this, and stuff is good. So this is actually not too bad. The problem somehow is that now you have a little bit of a different behavior, right? So instead of adding 2 things, right, instead of being in position or adding an edge meant that you have to have 2 things here, now we only have 1, right? So it's a little bit different behavior, but here, right, at least we can do it, right? So that's a nice thing. So we have definitely our self loops, right? This is definitely supported. Last thing there is parallel edges. Remember, it didn't work out for us too well with the matrix. So how does it work out here? This time it's actually going to be pretty straightforward. Because if I want to have a parallel edge, that means I have a node basically occurring in the adjacency list twice. So let's say I want to have 2 links between 0 and 1. What ends up happening is I add it, in there in my diagram, and over here in my picture, I basically add it like this. So now all of a sudden I go to 0. Now all of a sudden I go to, well, okay, one was already connected to 0, but my second 0. Right? I have basically that, right? So it's like I'm adding another entry on each of their adjacency lists, right? And that's pretty straightforward to do. Obviously, lists I can add as many elements to them as I want, right? Without having to worry about any sort of limits, right, or problems with it. So it's reasonable for me to add that parallel edge. So that works out fine as well. All right, so this is kind of our concept for an adjacency list. Let's take a look now at the source code that would be used to actually implement this thing. So here I have my code, right? And so this, is going to be pretty good stuff here. So it's not, well, it's not complicated. It's not hard to understand. That's kind of the point. That's what we like. Nothing special is actually a good thing, right? When you don't have to fight with the code and try to understand what it is. So let's just try parsing through it line by line, and it should be relatively straightforward. First, right, we have the number of vertices, which is final because it's fixed. Then we have the number of edges, which may change because we add edges over time. Then we have our adjacency list array, right? So this is basically that outside array that stores all of our linked lists, right? So that's this thing, right? That's called ADJ, right? It stands for adjacent. So basically, it's like I have an array of all the adjacencies of all of the nodes in my graph. And all that thing is really is basically it's an array of linked lists where the linked lists are containing integers, right? So it's pretty straightforward. Next thing I have is a constructor. So my constructor is going to take in v. It's basically the number of vertices to create, right? So we said that when we create this graph for the first time, I basically have to define how many nodes are in it, right? I have to do that for the first time. And so that's what I'm doing in my constructor. So I'm saving v, right? I'm initializing e to 0 because I don't have any edges to begin with. And then I'm creating basically my new array, right? So my first line over here, this thing over here, is basically creating an array of linked lists, right? We create an array of linked lists, and then because just the way Java works, we have to basically go to every index into that array and add a new list at every position, right? So I'm adding a list, right, for every point, right? So it's like I have to basically insert these little stubs here, right, so that each one of these has something inside of it, okay? All right, so once we've been through this, we basically have, an array of the appropriate size with a bunch of empty linked lists, right? Then we can manipulate it. So V and E are simple. They just return the current values of V and E. Not bad. Add edge, right? So add edge takes in 2 parameters. It takes in V, it takes in W. And what it does is it basically goes to the adjacency list of each of those 2 nodes, right? It goes to V's adjacency list, goes to W's adjacency list, and adds the other, right? So over here you can see we go to V's adjacency list, and then we add to it W, right? We go to W's adjacency list and add to it V, right? And this add function here, in case you're wondering where that's coming from, that's basically coming from the fact that these are linked lists, right? So I have, at each slot here, right, each of these is a list, right? So I'm going to that list and saying .add, and I'm giving it the number of the node that I'm wanting to add to it, right? So that's already built in functionality because I'm using lists to store the adjacencies for each of the nodes in my graph. All right, so I add them on both sides and increment e by 1 to represent that I've added a new node. Again, there's this weird thing that because it's undirected and I can go back and forth either direction, I'm basically having to add 2 of them, even though it's really just 1 edge. So the last thing we have here is going to be our adjacency method, which is ADJ. And basically what it's supposed to do is supposed to return a list or an iterable of all the nodes that are adjacent to another node. Turns out it's actually really simple to do here because all you do is you return the list, right? So it's like, well, if I want to know who's adjacent to V, let me just return the list at the Vth position inside the array, right? So I look inside that array, I look at that Vth position, and return what's ever there, right? So I return, maybe I return that one, right? That list that I have, right? And then the outside world can see that and can see, who is basically able to, who is adjacent to it, right? Who is next to it. Note here that when we do this, we're passing a list out, and it's fair game to do that because that list is in fact an iterable, right? It implements the iterable interface. And then, right, in addition to that, right, there's somehow a thought there of, the outside world will only see it as an iterable. It won't actually know it as being a list, right? So people won't be able to change it, right? Which is a nice thing. We don't want to give somebody the adjacency list for something and then they change it, right? We don't want that. But it's fine here because we just return an iterable, so the outside world just sees an iterable. All right. So kind of a conclusion here in the bottom left is our performance. So we have our adjacency matrix, we have our adjacency list, how they look, right? So space, right? V squared for matrix, V plus 2e for a list. Adding edges is constant time for both of them, right? Because these are lists, right? So it's easy to throw something in the beginning. For the matrix, right? So just go to the position, done. Check to see if something's adjacent. That's pretty easy for the matrix because you can just go again just right to the slot. But then for us, it'll be a little bit harder. If I want to know if two things are connected, what happens is I have to go to one of them, look at the adjacency list, then loop over and go one by one and check to see whether the thing I want is actually there or not. So it's a little bit more expensive. It ends up being, the degree of V, right? So I got to go check all your neighbors if I want to know if you're connected to a specific one. Last thing here is iterate adjacent. So for the matrix, if I want to go over your adjacency list, right, if I want to see everything that's next to you, I have to basically loop along one whole row in that matrix, right? So that's going to be V number of things. Whereas over here, let's say I want to look at all of your adjacent ones, I just look at the degree of that node, right? So here, right, those lists only have nodes that are next to you. They don't have any nodes that aren't connected. So it's going to be like a small number, right? Rather than having to go to the matrix and looking at the entire row and everything that's there, here I just look at the list. So if I'm looking at adjacent ones, I'm really just looking at the adjacent ones. I'm not looking at the ones that aren't connected, which I would be in a matrix. All right, so that's it for our performance here, right? So you can see, right, that these are both, I mean, they both implement the same thing, right? But again, right, typically, lists win just because of that space usage, right? That space usage is a lot better, right? Linear is way better than quadratic, so typically people just use lists. So as far as we're going to be concerned, right, for most of the programming we'll do in this class, we will be, well, for programming, right, in homeworks, we'll generally be sticking to a list representation, right? That's most efficient. The matrix representation, you should understand, you should know how to deal with it. But again, right, we don't see it in practice, so I probably won't. So I won't ask you for it on a homework, right? But you should know it. All right. So now that we're at this point, right, we have some good ideas, right, about how to implement this data structure. Next big topic for us in future videos is going to be algorithms that actually can go and query this and try to give us interesting answers. So I will see you guys in those videos.